Thank you. And thank you all for coming. It's a pleasure to be here in Vienna. And I understand I am one of the last speakers in this conference, and so it is my duty and honor and privilege and pleasure to thank the organizers. So. All right, so I will talk about some work which is joined with one of our absentee organizers, Sam Kim, and Javier here. We're both at KIAS in Seoul. So I'll start with giving some motivation for why I was interested in in the stuff that I'll be talking about today. That's more sort of groups acting on manifolds, and then motivate some of the more logical things. So if we consider, let M be a smooth, compact manifold. Maybe let's just assume it's connected manifold. Okay. Then it may or may not have boundaries, so I'm not going to assume that it's closed. And so we have, of course, the group of homeomorphisms of M, which is something that'll be of particular interest for me in this talk. And inside of this, we have groups of diffeomorphisms that are C1 diffeomorphisms, and inside of that, we have C2 diffeomorphisms and so on. And sometimes if you have further structure, you can put more stuff there. And so the motivating question for me is how one can distinguish between these groups in some finitary or combinatorial way, which is to say, by studying maybe their finitely generated subgroups, maybe at least countable subgroups, and also later through more model theory motivated invariance. So maybe the place where I'll start is a theorem which is due to Kim and someone else. So it says that so let the dimension of M be equal to 1, and let R be any real number between 1 and infinity. So then there exists a finitely generated group, gamma sub R, such that the following hold. So the first is that gamma R is a subgroup of diff R of M. Okay, so here for non-integer regularities, what I mean here by diff R is you take the floor function, so this is some integer, and then you take the CK diffeomorphisms, which are epsilon Holder continuous, where epsilon is just R minus K, the fractional part. Okay. So the interpolation between these diffeomorphism groups with integer regularities. Second is that the commutator subgroup of gamma R is infinite and simple. And the third conclusion is that any CS action of gamma R on M, where here S is greater than R factors through an abelian group. So any such action, okay, because the commutator subgroup of gamma sub R is infinite and simple, any smoother action of gamma sub R on the manifold M automatically has an enormous kernel. So in some sense, these groups gamma sub R, of which there are many, many, many examples. For each R, you can find continuum many with this property. And they're all, you can also like cut off the number of generators you need to something like 5 for the interval and 7 or 9, I think maybe for the circle. So you have many, many finitely generated subgroups that are distinguishing in some precise sense between these diffeomorphism groups, at least in dimension 1. Okay. So the question then that's going to motivate the rest of the content is what can be done in higher dimensions. So as is sort of already suggested by the way I'm asking this question, trying to get a theory like this to work in dimensions 2 or higher seems to be at least much harder than in dimension 1. One of the main reasons being that even though there's a lot of very interesting stuff that one can say about dynamics in 1 dimension, it is significantly simpler than the dynamical phenomena that occur even in dimension 2. And so, I mean, if one wants to produce groups like this that are distinguishing between diffeomorphism groups of various regularities, one can be fairly explicit in the 1-dimensional case. You can even write generators down almost explicitly in coordinates and then argue directly that they have the properties that you wish them to have. So for a question like this, so what can be done in higher dimension? So, I mean, the even more basic question is, so what are potential candidates? For groups which might have these distinguishing features. So that now motivates the remainder of what I'm going to talk about today. So the answer, at least for us today, will be subgroups of homeomorphisms of M and various diffeomorphism groups of M coming from model theoretic ideas. So let's explain what this means. Okay, so for now, let me forget that we had a smooth manifold. Let's just consider the case of a compact topological manifold. So, okay. So the diffeomorphism groups don't really make any sense. We concentrate on the group of homeomorphisms of M, and this group is very, very big. It's infinite dimensional in any sensible way that one can make sense of this word. And I mean, if you try to get your hands dirty with it, one finds that it's the diversity of subgroups inside of it, the structure is mind-boggling, and it seems difficult to find any patterns, at least in, I mean, dimension 1, you have some things to hold on to. In dimension 2 and higher, not really. So, but what can one say about the homeomorphism group of M? Well, maybe the first question is, what is the relationship between homeo of M and the underlying manifold M? So does homeo of M, for instance, determine M up to homeomorphism? And the answer is yes, right? So that's a theorem of Whittaker from the 1960s. And so what this theorem says is that, so if phi from homeo of M, you can even take the identity component of M, doesn't really matter, to homeo 0 of N is an isomorphism of groups, any isomorphism. So just not respecting the topology necessarily of the group homeo of M, then phi is induced by a homeomorphism of M and M. This is to say, in some sense, like if you want to compute what phi is, well, there's some hidden homeomorphism between M and N, so that if you compute phi on some homeomorphism in here, its value here is essentially conjugating that homeomorphism by the secret homeomorphism between M and N. So this is also true for diffeomorphism groups, at least of integer regularities. So this is Hawkins, Faulkner-Montgomery, also Rubin should be mentioned here, and Filipkiewicz. Great, so that's it, right? So that the manifold is completely determined by its homeomorphism group. Well, I mean, if you try and talk about a homeomorphism group and an isomorphism of it with some other homeomorphism group, this is a very, very unwieldy piece of data. So it would be nicer if you could have something that you could hold in your hand, some finite certificate, say that M and N are or are not homeomorphic to each other from just the group theory of homeo of M and homeo of N. So that's where the first order theory of homeo of M comes in. So for this, we consider homeomorphism groups in the language of groups. So as structures in the language of groups, which has just two non-logical symbols. Right? So it has a constant one, which is interpreted as generally as the multiplicative identity. Okay. And a binary operation, which is generally interpreted as the group operation. And then what one does in first order theory or in first order logic is one studies formulae and sentences that can be written in the language of groups. So you have sort of the usual logical symbols, which are or, and, not, implies, and well, equality, whether that's a logical symbol or not, is a bit of a matter of debate. And also universal and existential quantification. So I won't talk too formally about what's meant by talking about first order formulae or first order sentences in the language of groups. That would eat up way too much time. And although I think the intuition of what's meant here is fairly clear, what first order means is that when you are expressing statements, so writing down a formula or a sentence, which may or may not have variables in it, then the variables are only allowed to take values as elements in the underlying structure and not as subsets. That's what distinguishes first order theory from second order theory. So as an example, you can write something like phi ab, which is just the sentence that says for all x, for all y, x times y, oops, is equal to y times x. Okay. And this is a perfectly good first order sentence in the language of group theory. Is simply expressing that for any pair of elements in a group, they commute with each other. Okay. And what would not be an example would be, for all subgroups or something like that. That's not allowed a priori, because then if you're quantifying over subgroups, you're implicitly quantifying over subsets of the underlying group. A priori, this is not allowed. Okay. So then when you talk about the first order sentences and formulae that you can write in the language of groups, you can talk about, in some precise sense, the theory of a group. So informally, you write something like the theory of G, and this simply consists of the sentences which are true in G. Okay. And so in particular, you have something like B ab lies in the theory of G, or equivalently, one writes G is a model of the sentence phi ab if and only if G is abelian. Okay. So that's all I'll say about the formalities of first order logic. And I'll talk about the structure of the first order theory of homeomorphism groups in particular. So now if you have two, say, groups which you know are isomorphic to each other, then they have to have the same theory. So the isomorphism, you transfer the meaning of a variable in one group to the meaning of to its meaning in the other group via the isomorphism. So a sentence is true in one if and only if it's true in the other. Then you can you can weaken the notion of equivalence in this sense. So you can say, well, what if two groups have the same theory? Does that mean that they're isomorphic to each other? So that gives rise to the notion of elementary equivalence. So we write G is elementarily equivalent to H by definition, if and only if the theory of G is equal to the theory of H. Okay, so this is now an equivalence relation on groups, which is a priori coarser than isomorphism between groups. And it is actually coarser. So one example is the theory of finitely generated non-abelian free groups. It doesn't depend on the rank. As a consequence of the resolution of the Tarski problem due to Olga Harlampovich, Alexei Myasnikov, and Zlil Sela. So then the theorem that we'll start out with is the following. So let M be a compact manifold. So again, just a topological manifold. It need not have a smooth structure. So then there exists a sentence, P sub M, in the theory of homeo. In fact, you can write it as homeo of zero or the full homeomorphism group. It really doesn't matter. This is true for any subgroup which lies between the identity component and the full group of homeomorphisms. So there exists such a sentence such that if P sub M lies in the theory of some other homeomorphism group of a manifold, then M is homeomorphic to N. So in particular, being elementarily equivalent and isomorphic are the same notion for homeomorphism groups of compact manifolds. This is actually this phenomenon, it falls under the name which is in the title of my talks. This is called first order rigidity. In fact, it's actually something stronger because we don't have to compare the entire theories of homeo of M and homeo of N. This is actually called something called quasi-finite axiomatizability. Because within the class of homeomorphism groups of manifolds, the homeomorphism group of a particular manifold is finitely axiomatizable. So note that this resolves a conjecture which is due to Rubin in 1989. So there was a paper that appeared in Transactions of the AMS, where Rubin claimed that if you have two manifolds without any assumptions and they were elementarily equivalent, so the homeomorphism groups are elementarily equivalent to each other. And if you assume this certain axiom about set theory called Gödel constructibility, then M and N had to necessarily be homeomorphic to each other. And no proof appeared in the literature. And so this is the best that we can do now. There are some issues with the completely general case of non-compact manifolds. For instance, one is that the interval, closed interval and the real line have isomorphic homeomorphism groups. And so in particular, they are elementarily equivalent, but the two manifolds are not homeomorphic to each other. Okay, so connect this with the original motivating question. So let me state a theorem that's maybe in progress. So maybe I'll stick to just to conjecture for now. It's mostly proved. So, but if M is a smooth manifold, then also compact as before. I just won't write that again. So then, and there exists a sentence P sub M K in the theory of K times differentiable diffeomorphisms of M, such that if N is smooth and phi M K is in this theory as well, if L of N, then K is equal to L, and M and N are diffeomorphic. So something very similar would also be true for diffeomorphism groups. This is almost certainly true, and we're hammering out the details, but okay, so what is sort of the main takeaway is that these homeomorphism groups and diffeomorphism groups of arbitrary smooth manifolds have this sort of finite syntactic invariant that nails them down. So that's nice because, but I was really interested in an algebraic invariant, the one that ultimately gives you a group of some sort. So
tell me what phi is.
in principle, yes. In practice, it wouldn't be very fun. I mean, if you, I mean, so what phi is really saying? So I won't get into the proof of the theorem just because I don't really have enough time for that. But the point is that the theory of homeomorphism groups is extremely expressive, and so you can say something like, what is phi sub M saying? Well, phi sub M is saying that M is a manifold of a particular dimension, say n, okay, and it's covered by, say, some number of balls, say 5 Euclidean balls, okay, and there's also an embedding of so there's a particular function, right, from a ball into some high dimensional Euclidean space, so that if I take an embedding of M into, say, some Euclidean space of 1/5 that dimension, and then restricts to the ball separately, take the product map, and I get a product, I get a map from a single ball into that same high dimensional Euclidean space, so that these two maps from the ball are close to each other. That's what phi sub M is saying. And so then one then relies on this lemma that appears in a paper of Cheeger and Kister that says that whenever you have two such maps that are very close to each other, then the underlying manifolds are homeomorphic to each other. That's basically what's going on there. And that's what phi sub M is saying. I don't know if there's something simpler that one can say, except for maybe in dimension 1. In dimension 1, you can say something like, there is like a connected regular open subset, for example, that separates the manifold into two pieces. That's only true in the interval. Or maybe that there's a regular open subset with exactly two components that separates the manifold into two pieces, but not a connected one that does that. And that's true only in the circle. But for two-dimensional manifolds and higher, I'm not sure if you can do something simpler. Okay, so what I wanted to do is to pass from sort of syntactic invariance to algebraic ones which are actual groups. So how might I do that? So to pass between these syntactic invariants and groups, I'll appeal to one general result from model theory. So here's a proposition. I'll say it as a proposition because it's not the full theorem. So if X inside of the homeo of M is countable, just an arbitrary subset, then there exists a subgroup G inside of homeo of M such that G is countable, X is contained inside of G, and G is elementarily equivalent to homeo of M. And this is nothing special about homeo of M or even about groups. I mean, this is called the downward Löwenheim-Skolem theorem. So you could replace homeo by diff K if you like. You would get the exact same conclusion. And one consequence of this theorem is that if you have two different manifolds and you build these countable subgroups that are elementarily equivalent to the whole homeomorphism group, they are not isomorphic to each other. So they're different groups. They cannot be isomorphic to each other because they do not have the same theory. So here's the conjecture, which is supposed to be an answer to what are the potential candidates, which we don't really have that much of an idea of how to prove this in general. We can prove it in some cases. So if gamma sub R is a subgroup of diff R of M, which is also elementarily equivalent to it, then in any CS action of gamma R on M for here S greater than R is trivial. This would be ideally what would be the case. And so there are many, many questions. And so, for instance, can gamma R be finitely generated, for example? It's not obvious whether it can or cannot. Turns out that homeomorphism groups and diffeomorphism groups of manifolds have this amazing property called the Schreier property, that any countable subset of a homeomorphism group, for example, sits inside of a finitely generated subgroup. So maybe, I don't know. So then in my remaining time, I'll say a few more words in a slightly different direction about what one can do with the first order theory of just homeomorphism groups, not diffeomorphism groups necessarily. So here's a theorem that's true. So the theory of homeomorphism groups, I'll just say, maybe not the theory, I'll just write homeo of M interprets something called weak second order logic. So what does this mean? So that means two things. So that means the homeomorphism group interprets arithmetic. So that is to say, so actually it interprets more than just first order arithmetic, which is standard arithmetic. It actually interprets second order arithmetic. So you can talk about first order analysis even inside of homeo of M. That's sort of an essential part of the proof of this theorem. And it interprets hereditarily finite subsets. So if you'll recall, when I was talking about what the difference between first order and second order logic was, and it had to do with what values the variables were allowed to take. So can they take on values that are elements, or can they be subsets of the underlying structure? Well, it turns out that you can directly quantify by expanding the language suitably in a conservative way certain subsets. So hereditarily finite subsets are ones that are as follows, right? So you take so P0 of, I'll just write G for the group, so I don't have to write homeo over and over again. These will be finite subsets of G, and then Pn+1 G will be finite subsets of Pn G, and then the hereditarily finite subsets of G will be the union. All these things, right? So you can talk about sets which are finite collections of finite collections of finite collections of finite collections of finite elements, or something like that. As many iterations as you wish. So this sounds rather technical, but it has some consequences which are very useful. Well, I mean, useful is debatable, because you can't really decide the truth of any sentence a priori in a homeomorphism group, because precisely it interprets arithmetic, so Gödel's incompleteness gets in the way. But you can say a large number of different statements with mathematical content inside of the homeomorphism group. So in the last minute, I'll say one or two things, right? So there's a sentence that is true in, say, homeo of S1, if and only if there exists an infinite property T group, property T subgroup of homeo S1. Or you could say, right, there is a sentence which is true in homeo of a two-dimensional manifold, sigma, depending not on sigma at all, it depends on nothing in this statement here, which is true if and only if the mapping class group, sigma, is linear. I mean, of course, as I just said, like, you will not be able to feed these sentences to a computer and then prove or disprove the linearity of mapping class groups, unfortunately, but it still can be expressed as some finite length sentence and as simply a consequence of the interpretation of weak second order logic. I'll stop here.